Good morning, everyone. I am Garima from BSc Chemistry Honors, second year. Today, we are going to start our chapter Alcohols. Introduction. Alcohol consists a class of compounds which are regarded as hydroxyl derivatives of hydrocarbons. They are further classified as mono, di, and trihydric alcohols accordingly as the number of hydroxyl groups present in their molecules is 1, 2, or 3 respectively. Alcohol consisting 4 or more hydroxyl groups are known as polyhydric acid alcohols. Thus, we have monohydric is methyl alcohol, dihydric glycol, trihydric glycerol, and polyhydric sorbitol. It may be pointed out that di, tri, and polyhydric alcohol also have the OH groups attached to different carbon atoms. This is because a compound having two more than one OH group linked to same carbon atom is unstable and at once eliminates the element of water as shown below. Aromatic hydroxyl compounds fall into two categories. First, aromatic alcohols. These are the compounds in which the hydroxyl groups is present in the side chain. These may be regarded as alcohols in which OH group is attached to an aryl substituted alkyl radical. An important example of such a compound is benzene alcohol, phenol. These are compounds which consist hydro hydroxyl group or groups directly attached to an aromatic ring. For example, phenol is an important phenol. The per properties of a phenol are marked differently from the properties of alcohol, and their chemistry is discussed separately in chapter 2. Monohydric alcohols. These are the alcohol having general formula ROH, where R is a simple or substituted alkali group. Thus we have saturated monohydric alcohols are also known as alkanol, as there are derivatives from alkanes by the replacement of a hydrogen atom by a hydroxyl group. Alcohols can be represented by the general formula CnH2n plus 1 OH, where N is the number of carbon atoms. Classification. Monohydric alcohol may be further classified as primary, secondary, or tertiary alcohol as given below. Primary alcohol. These are alcohol in which hydroxyl group is attached to primary carbon atom. For example, ethyl alcohol and propyl alcohol. It is apparent that the carbon which carries the OH group has at least two hydrogens in it. In other words, primary alcohol have the characteristics group CH2OH present in them. Secondary alcohol. These are alcohol contain the hydroxyl group attached to the second carbon atom. For example, isopropyl alcohol. Tertiary alcohols. These are alcohols in which hydroxyl group is attached to tertiary carbon atom. For example, tert-butyl alcohol. It is clear that the carbon carrying OH group has no hydrogen attached to it. Nomenclature of monohydric alcohols. They can be named by three different systems. The common system. According to this system, which is used for the simplest alcohols are named by adding the word alcohol to the name of alkyl group present in the molecule. For example, methyl alcohol, ethyl alcohol, and propyl alcohol, benzyl alcohol. However, the IUPAC system, in this system, alcohols are named in accordance with the general IUPAC rules. The main point involved in the nomenclature are summed below. First, the longest chain containing the carbon atom carrying the hydroxyl group is selected, corresponding to the parent chain of carbon atom is numbered from that end, which gives the lowest possible number to carbon carrying the hydroxyl group. The name of alcohol is then written as one word by writing the name of the side chain or substituent along with their position in alphabetic order, followed by the name of parent alcohol. For example, ethanol 2-methyl propane 1-ol, 2-methyl propane 2-ol, butane 1-ol. Method of formation. Reduction of carbonyl compounds. Alcohol can be easily obtained by the reduction of aldehyde, ketone, carboxylic acid, etc. by a variety of reducing agent as discussed below. First, reduction of aldehyde and ketone. Aldehyde can be reduced by primary alcohol or ketone to secondary alcohol in a number of given ways. For example, a propanaldehyde in the presence of N-nickel will give N-propyl alcohol. Catalytic hydrogenation of an aldehyde or ketone containing other easily reducible groups such as carbon-carbon double bond will furnish products in which both functional groups are reduced. For example, croton aldehyde plus H2 in the presence of nickel will give N-butyl alcohol. B. Reduction with complex metal hydrides. The reduction of aldehyde and ketone to prepare alcohol is usually carried out in laboratory with the complex metal halide such as LiAlH4 and NaBH4. Sodium borohydride is easier to handle and can be used either in water or alcohol solution. The reduction product initially formed get hydrolyzed to form alcohol. For example, butanol in the presence of NaBH4, ethanol and H3O positive will give butane 1-ol. Mechanism. Reduction of aldehyde and ketones by both LiAlH4 and NaBH4 occurs through the nucleophilic attack of a hydride ion on the carbonyl group to form a complex containing add OB or OAL bond. This species has still got 3 metal hydrogen bonds and react further with 3 more molecules of carbonyl compounds. The metal alkoxide intermediate thus formed is hydrolyzed to give the alcohol as shown below. Reduction with NaBH4. NaBH4 will give Na positive plus BH4 negative. Then aldehyde or ketone will react with BH4 negative. 1H will the bond will move towards oxygen in the carbon oxygen bond, and this H from BH4 will go to carbon atom, so we will get the another product. Then we will take 3 ketones, that is 3 carbon double bond O, and the further reaction will carried out in which we will get metal alkoxide, which will further give alcohol. Same will be carried out with LiAlH4. Third is Mervin Pondorf-Valley reduction. It is commonly used reduction for the ketones to secondary alcohols. This reduction is carried out by heating the carbonyl compounds isopropyl alcohol in the presence of aluminium isopropoxide and dissolving of acetone from the reaction mixture. The other functional groups, if any, present in the carbonyl group remain unaffected. It is a reversible reaction, but the equilibrium is pushed in forward direction by dissolving the alcohol as soon as possible. Second, reduction of carboxylic acid. Primary alcohols can be obtained by the reduction of carboxylic acid by lithium aluminium hydride. In the reaction, the carbonyl part of carboxylic group is reduced to CH2 group. For example, butyric acid in the presence of LiAlH4 and ether second H3O positive will give 1-butanol. Mechanism. The reduction takes place through the formation of intermediate alkoxide which helps in the alcohol on hydrolysis. 4RCOH plus 3 LiAlH4 will give RCH2O4 ALLI, then in the presence of H3O positive it will give RCH2OH. This method is generally employed for the preparation of alcohol from acids which are readily available from natural sources. Carboxylic acid can also be reduced rapidly by primary alcohol by the action of diborane. Reduction of ethers. Reduction of ether consists of a convenient method of preparation of alcohols. The reduction is generally carried out by the following method. First, Bovilt-Blake reduction. This method involves the reduction of ether to alcohol by the treatment with sodium in alcohol. The reaction leads to the formation of a mixture of two alcohols in which is formed from alkoxide group and the second which is formed from the alkyl group. B. Reduction with LiAlH4. Ethers can also be reduced with LiAlH4 to yield a mixture of alcohols. For example, ethyl butyrate in the presence of LiAlH4 ether, second H3O positive will give 1 butanol plus ethanol. Mechanism. This reaction takes place by the addition of hydroxyl ion to the carbonyl group of ether groups. This is followed by elimination of alkoxide ion to yield an aldehyde intermediate. Further reaction of LiAlH4 with aldehyde gives a primary alcohol. This mechanism is given here. Third, catalytic hydrogenation. On the industrial scale, aldehyde are obtained from ethers by catalytic hydrogenation in the presence of copper chromide catalyst. For example, ethyl propanate in the presence of copper chromide will give prop-1-ol and ethanol. Fifth, oxymercuration, demercuration of alkenes. It is a very convenient two-step method for preparing alcohols from alkenes. When treated with mercuric acetate in a water tetrahydrofuran solution, alkanes form organic mercuric compound. These mercury compounds are reduced by sodium borohydrate to yield alcohols, that is alkene plus H2O plus mercuric acetate. In the presence of THF, oxymercuration will take place and we will get organomercurial compound. Hydroboration oxidation of alkenes. When treated with diborane, alkenes undergo hydroboration to form alkyl borate. The alkyl borate are readily oxidized by hydrogen peroxide alkaline solution to form alcohol. Thus, the net result of this reaction also is the addition of water to alkene to form alcohols. For example, ethylene plus BH3 twice will give ethyl borate. In the presence of ethene, it will give diethyl borate. Then another ethene, it will give triethyl borate. The overall reaction may be represented as ethylene in the presence of BH3 twice and H2O2 will give CH3CH2OH. Hydroboration oxidation is also an regioselective reaction, and the alcohol obtained is such as anti-Markovnikov addition of water to alkene has taken place. As such, this method can be used for the preparation of alcohols which cannot be prepared by other method of hydrogenation of alkene. For example, propylene in the presence of BH3 twice and H2OH with OH negative will give 1 propanol. It may be noted that due to anti-Markovnikov addition, only primary and secondary alcohols can be prepared by this method. Grignard synthesis. By far the most important method for the preparation of primary, secondary and tertiary alcohol is by the reaction between a Grignard reagent and a carbonyl compound such as a aldehyde or ketone. This addition product initially formed is decomposed with water, preferably in the presence of acids such as HCl or H2SO4 to get the alcohol. The general reaction may be depicted as follows. Carbonyl compound plus Grignard reagent in the presence of dry ether will give additional product. Then in the presence of H3O positive it will give alcohol. First, if the carbonyl compound used in the above reaction is formaldehyde, the final product is primary alcohol. Second, when the carbonyl compound used is some aldehyde other than the formaldehyde, the final product is secondary alcohol. For example, acetaldehyde plus CH3 MgI will give this product. Then we will get CH3 in the presence of H3O positive, we will get isopropenyl alcohol. Third, use of ketones to react with Grignard reagent leads to the ultimate formation of tertiary alcohol. It may be noted that in all these reactions, the number of carbon atoms in the alcohol obtained equal to the sum of carbon atoms in the aldehyde or ketones and Grignard reagent. 8. By the hydrolysis of alkyl halide. The hydrolysis of alkyl halide with a aqueous solution of sodium and potassium hydroxide or moist silver oxide results in the formation of alcohols. Alkyl halide plus aqueous KOH will give alcohols. 9th, by the hydrolysis of ethers. Hydrolysis of ethers with alkali solution is generally employed for the preparation of alcohols from naturally occurring ethers. For example, cetyl palmitate in the presence of aqueous NaOH will give sodium palmitate plus cetyl alcohol. 10th, by the fermentation of carbohydrates. This method may be used since very easily earlier times for the large scale preparation of ethyl alcohols. The carboxyde employed in the process is either sugar or some starchy material like potatoes, barley, rice or maize. Physical properties of alcohol. Due to the presence of OH group in their molecules, alcohols are polar compounds. Oxygen is more electronegative than either carbon or hydrogen, so that the electrons of the CO as well as OH group are displaced towards the oxygen atom. Therefore, the oxygen atom carries particle negative charge, while both carbon and hydrogen attached to the oxygen carries partial positive charge. Moreover, like water, alcohol molecules also has a band structure, so that we may represent alcohol molecules as R partial positive, ROH on O a partial negative. Because of this bond structure and polar nature of CO and OH bond, alcohol poses considerable dipole moment. The above structure features of alcohol has a strong influence on physical and chemical properties of alcohol as discussed below. First, physical state. The polar alcohols are colorless liquids, have a distinct alcohol smell and a burning taste. The higher members are colorless, tasteless, waxy solids. Second, associated state. Hydrogen bonding. Since alcohols contain a hydrogen attached to strongly electronegative oxygen, extensive intermolecular hydrogen bonding exists between alcohol molecules. As a result, alcohol exists in the form of associated molecules and not simply monomeric molecules. Third, boiling point. The boiling point of alcohols are much higher than those of hydrocarbons or ethers of comparable molecular weight, as is depicted from the following example. And their molecular weight and boiling point are given of some compounds. The higher boiling point of alcohols can be explained in terms of extensive intermolecular hydrogen bonding in alcohols. Large amount of energy is required to break these hydrogen bonds which hold the alcohol molecule together in an associated state. Therefore, alcohol boil at a much higher temperature than alkanes, ethers, etc., which do not form intermolecular hydrogen bonds. Solubility. The lower alcohols are highly soluble in water, but the solubility decreases with increase in molecular weight. The higher solubility of lower alcohol is due to the formation of hydrogen bonds between alcohols and water molecules. The rapid fall in the solubility of higher alcohol is due to the fact that with the increase in molar size, the non-polar hydrocarbon character of the molecule become more dominantly comparable with the polar OH group. This led to the decrease in extent of hydrogen bonding formation with water, and therefore the solubility in water decreases. For isomeric alcohols, the solubility increases with increase in branching. This is because of the reason that as the branching increases, the surface area of the non-polar hydrocarbon part decreases. The higher alcohol, it may be noted, are more soluble in organic solvent density. Generally speaking, the density of alcohol is less than that of water, although with increase in the molar weight. Chemical properties. The hydroxyl group present in alcohol is a very reactive group, and the characteristic reaction of alcohols are reaction of OH groups. In general, the reaction of alcohols may be divided into the following three categories. First, reaction involving the cleavage of OH group OH bond, reaction involving the cleavage of COH bond, and reaction involving both alkyl and hydroxyl group of alcohol molecule. First, reaction involving the cleavage of OH bond. The general order of reactivity of alcohol in this type of reaction is primary alcohol, then secondary alcohol, and then tertiary alcohol. Explanation. In the cleavage of OH bond, oxygen takes away the electron of a shared electron pair. Therefore, the reactivity of alcohol in this reaction can be explained in terms of electron releasing inductive effect of alkyl group. As we move from primary to secondary to tertiary alcohol, the number of alkyl groups attached to the carbon carrying the OH group increases from 1 to 3. Due to this, the electron density across oxygen goes on increasing on moving from primary to secondary to tertiary alcohols. This result is that the electrons of OH bond cannot be sufficiently drawn through oxygen, and the ease of cleavage of OH bond decreases. Thus, the order of reactivity in reaction involving the cleavage of OH bond is primary, secondary, and then tertiary. It can be easily understood that methyl alcohols would be more reactive of all alcohols. Reaction with metals. Acidic nature. Alcohol react with the active metals like sodium, potassium, magnesium, and aluminium to laminate hydrogen and form metal alcoholates or alkoxides. 2ROH plus 2M will give 2ROM plus H2. This reaction suggests that alcohol are acidic in nature. This is quite understandable since the OH group consists highly electronegative oxygen attached to hydrogen. Naturally, the OH bond is polarized in character and allows the separation of hydrogen as H positive ion. However, alcohols are very weak acid, even weaker than water. This is because the alkyl group present in alcohols present in Alkyl group present in alcohols have an electron releasing inductive effect. This causes an increased electron density around oxygen. This result is that electrons of OH bond are very not sufficiently drawn towards oxygen, and the release of proton is rendered difficult. In other words, the plus high effect of alkyl groups makes the alcohol weaker acids than water. Comparison of acidic strength of primary, secondary and tertiary alcohol. Since the plus high effect would be maximum in tertiary alcohol and least in primary alcohol, the order of acidity of alcohol is primary, secondary and tertiary. It is evident that metal alcohol would be stronger even than ethyl alcohol and other alcohols, since it has no alkyl group attached to carbon carrying OH group. Second, reaction with the Grignard reagent. Alcohols react with Grignard reagent to produce hydrocarbon as shown below. Alcohols plus Grignard reagent will give hydrocarbons. It may be noted that alkane formed corresponding to alkyl group of Grignard reagent. Third, reaction with organic acids. Alcohols react with organic acid to form ethers. This is slow reversible reaction termed as esterification. This is generally carried out in the presence of concentrated sulfuric acid or hydrogen chloride gas. Acid plus alcohol in the presence of concentrated H2SO4 will give RC double bond O R dash plus H2O. This reaction is reversible in nature, but the equilibrium can be pushed in forward direction by removing the water from continuously. This is done with the help of an apparatus called Dean and Stark separator. If esterification is carried out in the presence of HCl gas, it is known as Fischer-Spir esterification mechanism. The mechanism of esterification involves the initial protonation of the carboxylic oxygen of the carboxylic acid by the proton releasing by mineral acid. As a result, carboxylic carbon become more positively charged and readily undergo nucleophilic addition by the oxygen of alcohol. The resulting intermediate is ultimately converted into ester by depicted below mechanism. Isotopic tracker studies has confirmed that esterification involves the cleavage of OH bond and alcohol and COH bond of the acid as suggested by above mechanism. For instance, let us consider esterification reaction of acetic acid with ethyl alcohol having an isotope of oxygen of atomic weight 18 in the hydroxyl group. At the conclusion of esterification reaction, the isotropic oxygen would be found to be present in ester and not in water. Relative reactivities of alcohol and acid. The relative reactivity of alcohol and acid in the reaction are strongly influenced by steric hindrance caused by the presence of large group in them. The greater the size of groups near the OH group of alcohol or COH group of acid, the slower will be the esterification. For example, the decreasing rate of esterification of some alcohol and acids are given below. Alcohol CH3OH, then ethanol, then CH3 twice CHOH, then CH3 thrice COH. Reactions with acid halide or acid anhydride. When alcohol are heated with acid halide or acid anhydride, the hydrogen of OH group is replaced by acyl group and once again an ester is formed. The reaction known as acetylation takes place more rapidly than esterification with carboxylic acid themselves. Mechanism. The reaction mechanism may be depicted as below. With acid chloride, if we take RC double bond of Cl plus ROH, then O will attack on carbon. When the double bond between carbon and oxygen, one bond move towards O, and we will get further RCCl, and OR will attach on carbon and negative charge will be go on oxygen. Then the lone pairs move towards carbon, make two double bond, and Cl will be eliminated. At last we will get the product as RC double bond OR dash. Similarly it will happen for with acid anhydride. 1.6.2 Reaction involving the cleavage of COH bond. In this reaction, the bond between carbon of the alkyl group and oxygen of the hydroxyl group are ruptured. The order of reactivity of alcohol in this type of reaction is tertiary alcohol, secondary alcohol, primary alcohol. Explanation. The above order of reactivity can also be explained in terms of plus I effect of alkyl group. As we move from primary to secondary to tertiary alcohol, the number of alkyl groups attached to carbon carrying the OH group increases. Due to this, the electron of COH bond are pushed more and more towards oxygen. As a result, COH bond become more and more polar and therefore more reactive. In other words, tertiary alcohol would be more reactive in such reactions, and the reactivity will be lesser and still less in case of secondary and primary alcohols. It is also evident that methyl alcohol would be a least reactive of all alcohols. First, reaction with hydrogen halides. Alcohol react with hydrogen halides to form alkyl halide and water. ROH plus HX will give RX plus H2O. Hydrogen bromide and hydrogen iodide react in the same way as shown above in the case of hydrogen chloride, but without the presence of dehydrating agent anhydrous ZnCl2. The order of reactivity of halogen acid is Hi, then HBr, then HCl, while the order of reactivity of alcohol is tertiary, secondary, then primary. Due to the low reactivity, the reaction of hydrogen chloride with primary and secondary alcohol requires the use of catalysts such as anhydrous zinc chloride. Reaction with phosphorus halides. Alcohols react with phosphorus halides to yield corresponding alkyl halides. ROH plus PCl5 will give RCl plus POCl3 plus HCl. For example, ethyl alcohol plus Pi3 will give ethyl iodide plus H3PO3. Mechanism. The mechanism of the reaction between alcohol and PX3 may be elucidated by considering the reaction between an alcohol and PCl3 as given below. We have taken an alcohol and PCl3. One Cl will move out when O will attack on P, and we will get ROPCl2 and hydrogen attached on O. That is protonated alkyl dichlorophosphate. Then the Cl, which have negative charge, Cl negative, will attack on R, and we will get RCl plus HOPCl2. In the first step, nucleophile attack of alcohol on PCl3 takes place to form a protonated alkyl dichlorophosphate. In the second step, chloride ion act as nucleophile and displaces HOPCl2 from the phosphide initially formed. HOPCl2 react with more alcohols by the replacement of step 1 and 2 to form RCl and HO twice PCl. Further reaction between HO twice PCl and alcohols by step 1 and 2 gives rise to another molecule of RCl and OH thrice P or H3PO3. Thus the reaction ultimately leads to the conversion of 3 moles of alcohol and alkyl chloride by 1 mole of PCl3. Reaction with thionyl chloride. Alcohols react with thionyl chloride, preferably in the presence of a base such as tertiary amine, to form alkyl chloride. Alcohol plus thiochloride will give alkyl chloride plus SO2 plus HCl. For example, ethyl alcohol plus SOCl2 will give ethyl chloride plus SO2 plus HCl. The base promotes the reaction by reacting with HCl, that is tertiary amine plus HCl will give H3R3NH plus Cl negative. The mechanism is given below. Reaction involving both alkyl and hydroxyl groups. First, acetic dehydration. When alcohols are heated with sulfuric acid, phosphoric acid or boric acid, or when their vapors are passed out, heated aluminium oxide alcohol get dehydrated to form alkenes. For example, ethyl alcohol in the presence of H2SO4 we will get ethylene plus H2O, and butyl alcohol in the presence of H2SO4 we will get 2-butene plus 1-butene. Mechanism of dehydration. The mechanism of dehydration of alcohol involves the formation of a carbocation as an intermediate. The reaction is believed to take place in 3 steps. In the first step, alcohol combined with the hydrogen ion to form protonated alcohol or oxonium ion. The second step involves the dissociation of oxonium ion and formation of the carbocation. Finally, the carbocation loses a hydrogen ion to yield the alkene. The various steps are illustrated ahead with the help of ethyl alcohol. Ethyl alcohol plus from acid H positive will give protonated alcohol or oxonium ion. All the 3 steps shown above involve reversible equilibrium. However, the resulting alkene is much more volatile than the starting alcohol and is easily driven out from the reaction mixture. This shifts the equilibrium in step 3 towards the right. Consequently, the entire reaction is pushed to completion. It may be noted that the dissolution of oxonium ion requires the supply of energy. This is made available through the solvation of carbocation, considerably energy being released by the setting up of ion dipole bonds between the carbocation and solvent molecule. Relative ease of hydrogenation of alcohol. It has been observed that the ease of dehydration of different classes of alcohol followed the order of tertiary, secondary, then primary. This step involved transition state involved in it may be depicted as below. The positive charge, it may be noted, is originally on the oxygen, but in the product it is on carbon. In the transition state in which the carbon-oxygen bond is beginning to break, the positively charged is partially on oxygen and partially on carbon. This means that the transition state has acquired some carbocation character. As such, the same factors which increase the stability of carbocation would increase the stability of transition state, lead to that ion and lowers it EACT. This means that the transition state leading to the formation of a tertiary cation would be more stable and therefore has least EACT. In other words, such a transition state and the carbocation generated by it would be formed more readily. Consequently, the dehydration of tertiary alcohol would take place more readily. The dehydration of secondary alcohol, which involve the formation of less stable secondary cation, would naturally take place less easily. Similarly, the dehydration of primary alcohol involving the least stable primary cation would be more difficult. Conversion of secondary into tertiary alcohol: 3-methyl 2-butyl into 2-methyl 2-butanol. 2-methyl 2-butanol dehydration, we will get 2-methyl 2-butene. Then 2-methyl 2-iodobutane, we will, in the presence of AgOH, we will get 2-methyl 2-butanol. Isopropyl alcohol into tert-butyl alcohol. Isopropyl alcohol in the presence of K2Cr2O7, we will get acetone. Then in the presence of CH3MgI, we will get this. Then we will get tert-butyl alcohol when treated with H3O positive. The reaction is known as cis hydroxylation, as it proceeds into a steric specific manner leads to the formation of cis diol. For example, cyclopentane in the presence of KMnO4H2O, we will get cis cyclopentane 1,2-diol. Hydrolysis of epoxides. Glycol can also be prepared by the acidic catalyst hydrolysis of epoxy which involve the cleavage of epoxide ring. Epoxide plus H2 in the presence of H positive, we will get COH. Ethylene oxide plus H2O in the presence of H positive, we will get ethylene glycol. It may be noted that hydrolysis of epoxide is also stereospecific and due to the formation of trans diols. Epoxides themselves are usually prepared by treating alkenes with peroxy acids. For example, ethene plus peroxyformic acid, we will get ethylene oxide. Third, hydrolysis of dihaloalkane. Diols can be easily prepared by the hydrolysis of dihaloalkanes. Fourth, bimolecular reduction of carbonyl compounds. When treated with magnesium in an inert solvent such as benzene and ether under alkaline condition, aldehyde and ketone undergo bimolecular reduction to form vicinal glycol. This mechanism of reaction is discussed later under aldehydes and ketones. Here we have taken ketone in the presence of Mg or benzene. Second, H2O, we will get pinacol. Fifth, reduction of dicarboxylic compound. Diols can also be prepared by the reaction of dicarbonyl compounds such as monohydric alcohol can be prepared by reducing aldehyde in ketones. For example, butane 1,2-diol in the presence of H2 nickel, we will get butane 1,4-diol. Reaction of diketone with Grignard reagent. This method can be used for the preparation of higher vicinal glycol. For example, butane 1,2-diol in the presence of 2-RMGX and H3O positive, we will get 1,2-glycol. Physical properties. Physical state. Glycol are generally colorless, viscous liquids having a sweet taste. High melting point and boiling point. Glycol undergo intermolecular hydrogen bonding to a greater extent than monohydric alcohol. This is because they contain two sites for hydrogen bonding per molecule. As a result of extensive hydrogen bonding, glycols have much higher melting boiling point as compared to monohydric alcohol. For example, the boiling point of ethyl glycol is 470 Kelvin as compared to 351.5 Kelvin for ethyl alcohol. Third, solubility. Glycols have higher solubility in water than the monohydric alcohols. This is again due to more extensive formation of hydrogen bond between glycol and water than in between monohydric alcohol and water. Chemical properties. Like monohydric alcohol, glycol exhibit the usual reaction of hydroxyl groups such as the reaction with metals. At the same time, glycol undergoes certain reactions that are typical only of alcohols having two or more alcoholic groups. We will now illustrate the important reaction of glycol by taking vicinal glycol as typical example. Reaction with metal. Acidic nature. Like monohydric alcohol, glycol react with metal like sodium to form mono and disodium derivative and liberate hydrogen. For example, ethylene glycol in the presence of sodium 333 Kelvin, we will get monosodium glycolate. Then in the presence of Na, that is sodium 433 Kelvin, we will get disodium glycolate. It may be noted that the two OH groups react one by one. At the same time, the second OH group reacts slowly as compared to the first. This is because diol molecule, the electron attracting inductive effect of one hydroxyl group makes the other hydroxyl group more acidic in nature, and it reacts with the metal quite rapidly. But in the product form, in the first stage, the CH2O part exert an electron releasing effect which decreases the acidic character of second OH group. Reaction with hydrogen halides. It reacts with HCl and HBr to form two different products as shown below. Ethyl glycol plus HCl in the presence of 433 Kelvin, we will get ethylene chloride. Then HCl 473 Kelvin, we will get ethyl dichloride. It may be noted that first stage of reaction takes place more readily than the second. This may be understood in terms of mechanism of reaction. The reaction involves the initial protonation of OH group to form oxonium ion, which then undergo nucleophilic attack by halide ion Cl negative or Br negative to form the halo derivative. After the substitution of one OH group by Cl, the electron density around the oxygen of second OH group decreases because of strong electron attracting inductive effect of chlorine. As a result, protonation of second OH group does not take place easily. With Hi, diiodide formed decomposes to give alkene. For example, reaction with PCl5 or thionyl chloride. Glycol react with phosphorus pentachloride or thionyl chloride to form dichlorohalides. Reaction with phosphorus trihalides. When treated with PCl3 or PBr3, glycol form dichloride or dibromide. However, with Pi3, diiodide first formed being unstable decomposes to give alkene and iodide. Reaction with nitric acid. When heated with concentrated NO3 in the presence of concentrated H2SO4, glycol form dinitrate as shown by the example. Dehydration of glycol under different conditions give different product. It is illustrated below by considering the example of ethylene glycol. When heated to nearly 775 Kelvin, ethylene glycol form ethylene oxide as shown by example. When treated with anhydrous zinc chloride under pressure in a sealed tube, ethylene glycol get dehydrogenated to form acetaldehyde formed through arrangement of vinyl alcohol. Ethyl glycol in the presence of anhydrous ZnCl2, we will get vinyl alcohol that is unstable. Then rearrangement, we will get acetaldehyde. So here our chapter is completed. Thank you.